So the lesson objective is I can solve rational inequalities. Given a rational function f of x, a rational inequality has the general form f of x is greater than 0, f of x is greater than or equal to 0, f of x is not equal to 0, f of x is less than 0, or f of x is less than or equal to 0. So when f of x is greater than 0, this is true when f of x is positive, and when f of x is less than 0, this is true when f of x is negative. So here we have the graph of 2x squared minus 6x minus 8 over x squared plus x minus 6 to the right here. So we're going to name the intervals for which f of x is greater than 0. So I'm going to highlight first where f of x is greater than 0 on the graph. So we're greater than 0 here, here, and here. So that is from negative infinity to negative 3, from negative 1 to 2, and from 4 to infinity. And we're going based on the x values. So negative infinity to negative 3, and then we have a vertical asymptote here, which is why it doesn't go through. And then we have from negative 1 to positive 2, and then we have from 4 to infinity. So now we want when f of x is less than 0, so we're going to highlight those intervals. So that is from negative 3 to negative 1, and from 2 to 4. So if you notice, all rational functions switch signs at its zeros and vertical asymptotes. So to solve a rational inequality, you're going to move all terms to one side of the inequality, so 0 is on the other side. Find the zeros of both the numerator and denominator by factoring. Plot these points on a number line. The asymptotes always get an open circle because that's when the denominator can equal 0. And then we're going to choose points to test to determine when the intervals are positive or negative, and then we're going to write the solution using interval notation. All right, so we have x plus 5 over x plus 2. So we're going to figure out when the numerator equals 0 and when the denominator equals 0. So if x plus 5 equals 0, we have a 0 at x equals negative 5. And then if x plus 2 equals 0, we have a 0 at, we don't have a 0 at x equals negative 2. We have a vertical asymptote here. So we can go ahead and draw our number line. At negative 2, we have an open circle, and then at negative 5, we have a closed circle, and now we choose points around our values. So we're going to do negative 6, negative 3, and 0. And so at negative 6, the graph will be at negative at 1/4. So that's going to be greater than 0. At negative 3, the graph is at negative 2, so that's going to be less than 0. And at 0, the graph is going to be at 5 over 2, so that's again greater than 0. And we can figure these out by plugging in each of these values in for x. So it would look like this. And this is how we'd have it all written out. So then we want to figure out when we are greater than 0. So that's going to be so we have from negative infinity to negative 5, union with negative 2 to infinity. Here we have x over x squared minus 5x minus 6, and we want to know when this is less than 0. So we first set the numerator equal to 0. So we just get x equals 0, and now we set the denominator equal to 0. So we have a trinomial with a middle term as negative 5 and the third term as negative 6. So we need two numbers that multiply to negative 6 and add to negative 5. So that's going to be negative 6 and positive 1. So we'll have x minus 6 times x plus 1 equals 0. So x equals 6 and x equals negative 1. Now, when we plot these on the number line, x can never be these values. So we're going to include the negative 1 with an open circle, 0, and 6. And then we're going to choose values to the left of negative 1, negative 2, between 0 and negative 1. So we're going to do negative 1/2. And then we're going to have between 0 and 6, so we'll use 1. And then we have after 6, so we'll use 7. So now we can plug these values into our equation and see what we get. So if we test -2, we'll end up with -1/4. So that's going to be less than 0. Then we can test -1/2. So that'll be -1/2 over -1/2 squared minus 5 times -1/2 minus 6. And that'll, so we end up getting -0.06. So that'll just be negative. And then at 1, we have 1 over 1 squared minus 5 minus 6. And that's going to be 1 over -10. So that'll be also less than 0. And then we also will test the 0.7. So that's going to be 7 over 49 minus 35 minus 6, which is going to be 7 over 8, which is less than 0, which is greater than 0. So then we want to know when x is less than 0. So that'll be from -infinity to -1 union 0 to 6. All right, so here we have x squared minus 9 over x plus 4 is greater than or equal to 0. We'll first set x squared minus 9 equal to 0. Then we'll solve for x, and we get x is plus or minus 3. So then we have x plus 4 equals 0. So then we get x equals -4. So then we can test values around -3, -4, and +3. So I'm going to choose -5, -3.5, 0, and 4. And we can, at this point, you get the idea. You can plug them into the calculator, though, to figure out whether they'll be positive or negative. So at -5, we're going to be less than 0. At -3.5, we're going to be greater than 0. At 0, we're going to be, again, less than 0. And then at 4, we're going to be greater than 0. So when we are greater than, so when this function is greater than or equal to 0, we'll be from -4 to -3 bracket union 3 to infinity. And we're using brackets here because these are zeros. If we were using the vertical asymptotes, they wouldn't include them. So use brackets. And more importantly, it's because we have the less than or equal part. Here we have x minus 6 over x squared plus 10x plus 21. And we want to know when this is less than or equal to 0. First, we set x minus 6 equal to 0. So that's when x equals 6. And then we have x squared plus 10x plus 21 equals 0. So we're going to factor this as two binomials set equal to 0. We need two numbers that multiply to 21 and add to 10. So that's going to be 3 and 7. So we'll have x plus 3 times x plus 7. So x plus 3 equals 0. X plus 7 equals 0. So x is -3 or x is -7. Now we can check points surrounding these values. So we have -3, -7, and then we have 6. So I'm going to check -8, -4, 0, and +7. So at -8, we're going to be less than 0. At -4, we're going to be greater than 0. At 0, we're going to be less than 0. And then at 7, we're going to be greater than 0. So this graph is less than or equal to 0 from -infinity to -7, union -3 to 6. But we're not including, but we're including 6 because this is when f of x is less than or equal to 0. And x equals 6 is a 0. So you include your zeros. You don't include the vertical asymptotes. Unfortunately, I couldn't finish the video. I ran out of time, so I'm going to break this up into two of them. Here we have x squared minus 5x plus 4 over x squared plus 2x is less than or equal to 0. First, we set the numerator equal to 0. So we need two numbers that multiply to 4 and add to -5. So that'll be -4 and -1. So we have a 0 at x equals 4 and x equals 1. And then we're going to set our denominator equal to 0. So we get x times x plus 2 equals 0. So x equals 0, or x is -2. These are the vertical asymptotes. So then we go ahead and we plot the points and we check points surrounding them. So we have -2, 0, 1, and 4. So let's check the values. -3, -1, 1/2, 2, and 5. So at 5, the graph is going to be greater than 0. At 2, the graph will be less than 0. At 1/2, the graph will be greater than 0. At -1, the graph will be less than 0. And at -3, the graph will be greater than 0. So then we want when f of x is less than or equal to 0, that's going to be from only including the values -2 to 0, union 1 to 4. And we don't include -2, and we don't include 0.